Hello and welcome to the Statistics and Mathematics Tutors course on stochastic processes. So in today's video, we're going to look at martingales and Brownian motion. We first of all look at martingales in one video and Brownian motion in another. So, and simply put, for us, before we look at a martingale, we need to look at the concept of an algebra, then a sigma algebra. So from your elementary statistics, or maybe sets, your knowledge on sets from Cantor, we all know what a power set is. If you don't know, maybe you try to revise on that. A set, okay, set theory. So we know the power set should be the set that contains all possible subsets of the sample space, right? So here the sigma algebra or the algebra can be seen as an example of a power set. So we say that given a particular sample space omega, for us to have an algebra, then this omega should be a member of the algebra. The algebra is so big that it even contains the sample space itself, right? Or the empty set should be a member of the algebra. In other books you see this, right? You understand this soon. So if we have any event A which is a member of the algebra, then the complement of this event should also be a member of the algebra. If we have any two events A and B which are members of the algebra, then the union of these two events should also be a member of the algebra. These three definitions form that of an algebra, but for a sigma algebra it needs to satisfy the fourth condition, that is, if a1, a2, a3 all the way to infinity belongs to that of the algebra, that is like a partition, then the union of all these subsets, disjoint subsets, should also be a member of the sigma algebra or the algebra, which makes it a sigma algebra. Okay, now let's proceed by looking at some of the fundamentals in studying martingales. A martingale is like how will I say, it's like a market where it's like information that you have to predict a particular thing, right? So let's say you would want to you go to Google, you want to find the exchange rate of your country on Google. When you search for today's exchange rate, obviously you are going to maybe get some results from Google, right? That is because we have some information base or some database that is available on Google, that when you search you can actually get whatever that you want, whatever exchange rate from today and all the days before, like the previous days, historical data. You can get all the exchange rate over there. This is because we have an information that has been stored there. So that is what, so before we study martingale, which is like a game, or maybe we try to make the market fair for everybody, we want to know the information we have available in the market before trading or whatever can take place, like in the forest market or something. So imagine that we have some random experiment to be performed and the outcome is a particular omega, which is a subset of all possible outcomes, capital omega, as you can see here. Suppose that omega is a subset of 8 possible outcomes of 3 tosses of a coin, right? We all know if you toss 3 coins at the same time, you're going to get 8 possible outcomes, which is omega, right? So if we are told nothing at all, like we have no clue about the coin tosses, as in the first one is going to be a head or a tail, the second one is going to be a tail, and the fourth one is going to be whatever, we don't know. If we have no clue about the information set, then we are just minimal to the empty set and that of what? Omega. In other words, we have omega as our only set. But remember we said that for a sigma algebra, the if a set belongs to the sigma algebra, the complement of that should also be a member of the sigma algebra, which is the empty set of the sigma or the omega. Here is the empty set, and the union of the empty set and that of omega should be omega as well, which is there. So it means that F0 is our sigma algebra when we are given nothing about the coin tosses. We have no information, right? So this sigma algebra generated is called the trivial sigma algebra. That is, a sigma algebra that contains the empty set on omega is called the trivial sigma algebra. So now let's continue by refining our information set. Imagine we are told about the first outcome of the coin toss. We know there are 3 coins we are tossing. So if you are told the outcome of the first coin toss, then it could either be a head or a tail. If it's a head, then we are going to get head, 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 tail, head, tail, head, head, tail, tail. If it's a tail, remember, don't forget, you realize that the first coin toss is head in each of these, right? Meaning we have no information about the remaining 2 coin tosses. That's why we made it randomized by looking at all possibilities that those 2 coin tosses could be. The same way applies to being a tail. The first one will be a tail, but we have nothing at all. Like, we have no clue about the remaining 2 coin tosses, and that will give us this information set, right? So now we have 2 events, 2 possible outcomes, that is a head and a tail subset. So these outcomes are the first toss. Okay, so let's generate a sigma algebra. So we know that the sigma algebra should contain these 2 elements, right? The 2 sets are there. So AH is here, as you can see. AT is also there. Then we are saying that when you pick any 2 events, right? So the union of those 2 should also be in the sigma algebra. And remember, AH union AT should give us omega. So that's what omega is here. Now we realize that what is the complement of that of omega is the empty set. So that's why the empty set is over here, right? Now let's look at something. So you realize that F1 or F0 is a subset of that of F1 because F0 was containing only omega in the empty set, but F1 contains even the F0 itself. So that means that we can see that the previous sigma algebra is contained in the current one. Let's say that you are playing a game. Let's say you are playing Ludo, and in this Ludo we have rules that are being given to you. Maybe you don't know how to play at all. You don't know how to play the Ludo. So if I give you a first clue on how to play the Ludo, like how to move your stuff around, your marbles around in the Ludo, that's no problem. Maybe you are okay with the first rule and you can play a bit better than if no clue is given to you. If I give you a second clue, there's no way that maybe you're going to forget about the first one, or you say that the first one I've given you is insignificant. You're obviously going to use the first one to add up to the second one to make your information set so that you can play better. So that is why we are having the previous sigma algebra like contained in the current one, because it's like information and condition. Each information you pick is like you are adding it up to predict your random variable, or maybe to predict whatever you want to do accurately. So now let's say we are giving information on the first 2 tosses. We know that it could either be a head, or the second one will be a head, or the first one will be a head and the second one will be a tail, or tail head or tail tail. So if you do that, these are the possible outcomes you're going to get, right? We get 4 outcomes. Now let's see what will happen. So the sigma algebra over here is going to give us the first, that is going to be AHH, AHT, ATH, ATT. So you can see all of them are here. Now we say that when you have any element or subset at all in the sigma algebra, any subset at all, any element which is part of the sigma algebra should have its complement also in it. So that's why we have the 4 complements here, and you can see that none of these 4 complements are already included here, right? Now what is the union of all these 3? That's omega. And what is the complement of omega? Is empty set. So that's why these are there. Now let's look at pairwise union. The pairwise union, that is, if you have any 2 events which belong to the sigma algebra, then the complement of those, the union of those 2 events should also be a member of the sigma algebra. So we pick A HH union A HT. That's what you can see here. Then we pick the pairwise unions that you can see for all of them. We picked everything, and this is here. But now realize something. AHT union AHH is the same as AH from the previous sigma algebra. That's F1. So we can combine these two, and also ATH and ATT is the same as AT from the previous one. So we can summarize that F2 into this by making, okay, so this is okay, yeah, so we can make it like that, right? Yeah, so that's okay. Now you realize that once we make it, I mean, like AHH and AHH, and then we have, okay, sure, so I think it's here. I was looking for this simplification, that AH and AT are here, and you realize that the empty set omega, AH and AT were all part of the previous one, so that is very, very okay. And you can see that F1 can also be seen as a subset of that of F2, right? Good. So if you are told about all the three coin tosses, then we are going to get a very large subset, or the omega is going to be bigger. We are going to have around the 250 subsets of omega, and taking all together, that constitutes F3. That is the sigma algebra times 3. Yes, good. So now you realize that I told you that F0 is a subset of F1, and F1 is a subset of that of F2. The same way F2 is going to be a subset of that of F3. So this is seen, this collection, increasing collection of sigma algebra, as we filter the information, or as we sieve the information over time, adding more information to it for better accuracy and prediction, is called filtration. So an increasing collection of sigma algebras over time is called filtration. So if we have sigma algebras F0, F1, F2 and F3 indexed by time, as time moves forward, we obtain finer resolution, as in we get better out prediction, because more information is being added to us. So in other words, if I think this one is okay, if you have any n which is less than m, that means the time n is less than time m, then F substrate and the sigma algebra at time m contains more information than that of the sigma algebra at time n. So the collection of these sigma algebra is called filtration, like I mentioned. So this is a proper definition. You can look at it. So let omega be a non-empty set and t greater than 0 fixed. That's the time. That's the space available for our time for us to choose from. Suppose for each t which belongs to this interval, there is a sigma algebra ft if we have time s less than time t, and the sigma algebra at time s is a subset of that of the sigma algebra at time t, then the collection of these sigma algebra is called filtration. Okay, yeah. So let's look at measurability. So we say that a random variable is as a sigma algebra measurable if the sigma algebra contains every information that is necessary to predict that random variable, or the randomness in that particular random variable. That is what we call measurability on the sigma algebra, right? Good. So let x be a random variable on an empty sample space, that's omega. Let G be a sigma algebra of subset omega. If every set in X is also in G, we say that X is G measurable. That is, if X every subset, that means sigma algebra generated by X is actually like the sigma algebra that contains all the information to measure the randomness of X, right? Good. That's how measurability is defined. Great. So let's leave this one and move to conditional expectation. So we are saying that when a random variable is measurable with respect to a sigma algebra G, then the information in G is sufficient enough to determine the value of the random variable, like I said. So on the other hand, when a random variable is independent of a sigma algebra, then the information in G gives no clue about the value of the random variable. That means that is, if the random variable is independent of the sigma algebra, it has no clue to predict it. So that's independent. In the intermediate case, we can use the information in G to estimate but not precisely evaluate X. The conditional expectation of X given G is such an estimate, right? So in conditional expectation, let's say that we have a random variable X defined on the probability space, omega, sigma algebra, and then this probability measure notation, and a sigma algebra that is G, which is a sub-sigma algebra of that of the sigma algebra F. The conditional expectation of X given G, where X is either non-negative or integrable, the conditional expectation of X given G denoted this is the notation for conditional expectation, which I presume you know from your probability theory. Okay, is any random variable that satisfies number one, measurability. Yes, we've already mentioned measurability. Yep. So partial averaging, then you should satisfy this condition. All right, good. Partial averaging, don't forget. Yeah, that means the conditional expectation, okay, should actually exist in this form, right? Good. So let's look at some proposition on the conditional expectation. So we're going to look at some two random variables or two integrable random variables X and Y, which are integrable random variables such that the product is also integrable on the probability space. And we are going to take G and H to be two sub-sigma algebras in F, right? Then we have this. So if you have AX, A and B are all real numbers, constant real numbers. So AX, expected value of AX plus BY given the sigma algebra should be equal to, so we can break this into this, that's A, expected value of X given G plus B, expected value of Y given G. This is the linearity property of conditional expectation, don't forget. So we say that expected value of X given G should be equal to X if and only if X is G measurable. Then expected value of XY given G should be equal to X expected value of Y given G if X is G measurable. If X is G measurable, then it means that X or G has the necessary information to predict the randomness in X but not that of Y. For Y, we have insufficient information. We have no much information to talk about the relationship for now. Yeah. So if there's independence, that is, if X is independent of that of G, then it has nothing to do with that of G. So remember, if you have probability of A given B, if you have probability of A given B, if A is independent of that of B, then it simply will give us probability of B. Same thing here. So if X is independent of G, then the expected value of X given G simply will give us expected value of X. As simple as that. Okay. So this is like a tower property, or a double conditional expectation, right? Remember, if X is G measurable, the expected value of X given G should be giving us X. Then we are taking the expected value of it again. That will just give us expected value of X, right? Great. So this is a Jensen's inequality. It's not so important in our application level, so we can skip that, right? So let's look at martingales. So we see that everything we are doing is actually geared towards martingales, right? So we are saying that let this be a probability space, then a process MT is a martingale. A stochastic process M subscript T is a martingale if, number one, MT is adapted to filtration. Remember we spoke about filtration. That means an increasing collection of sigma algebras in this process. If that holds, then it's a martingale. Then we're saying that the absolute expected value of this martingale, okay, MT, should be less than, it should be finite, it should be less than infinity. Then we are saying that imagine S is actually today, right? That's time. S and T are all times. And then the sigma algebra is at time T, it's as of today. But we want to predict, let's say MT is actually the exchange rate at any point in time, right? So we are saying that MT should be a martingale if and only if, when you want to predict the exchange rate tomorrow, it should give you up to only today, because the sigma algebra S is today and T is tomorrow. So if we want to predict the sigma algebra tomorrow, that is t greater than s, it should be able to give us just up to a limited s. That is today, because if, let's say, somebody is able to know the exchange rate tomorrow whilst we all don't know, the person will take advantage of the market and it becomes an unfair market, right? So we want to make all market fair markets or martingles, because we want to make sure that it's a perfect market, that there exists no arbitrage, such that no arbitrageurs can take advantage of the market. Arbitrageurs are actually people who take advantage of the market. They make profit without risk, right? So imagine somebody is able to know the exchange rate tomorrow. Maybe his financial decisions will change from the rest of us who do not know. So if you go to Google today, ask for tomorrow's exchange rate, maybe they are going to give you today, because tomorrow, if they give you tomorrow's exchange rate, then it's not a fair market, because you are going to have some insider information about the market that we don't know, right? Yes. So same way, if somebody know about maybe, let's say you have the minister of agric as maybe your family relative or something, who knows about the prices of cocoa to be now is going to be let's say it's 4,000 cedis today, and next month we are going to increase it to that of 6,000 cedis, and you are aware of this information that nobody knows about. It means that the person who has the insider information about the increment in the cocoa prices is possibly going to buy cocoa from people who have it in stock right now and keep it. When the price goes up next month, the person is going to sell and make more profit, like 2,000 cedis profit on it. But imagine everybody had the same information, who will be willing to sell? No one. Yeah, so if something like that happens in the market, then it's not a martingale, it's not fair at all. So we want all markets to be a martingale. Yeah, so that explains this point. So this is what a martingale is. Okay, great. So we say that if this condition holds, then it's a martingale. But if it gives us a value, if that expected value gives us a value more than what we actually expecting, then it's a sub-martingale. Don't be confused. The greater than or equal to sign giving us a sub-martingale, that is what it is, right? And if it's less than or equal to our result, then it's a super martingale, right? Good. So let's try to see. We have a process mt equal to a Poisson process, that is nt minus lambda t, where nt is a Poisson process, like I said. So we want to confirm if this is a martingale. So we take the expected value and see. Every process is adapted to its natural filtration. So we normally don't check for this adaptedness, but we check for the expected and then the martingale condition, this last condition. So nt, expected value of this, so we can strike once expectation is a linear operator. This is expected value of nt minus lambda t, which is a constant. Remember, the mean of the Poisson process is nt. So the expected value of the Poisson process actually is going to give us nt as well, which will give us 0. Okay, so let's check the last condition. So to prove that mt is a martingale, then it means that mt is the same as nt minus lambda t, given this should be equal to what? ms, right? Good, let's see that. So all we need to do is to create and destroy within the Poisson process, the process that we have. Okay, that means that ns, so we're going to create and destroy. So we see that we have time s in it, so ns minus ns, so that will cancel out, is the same thing. But this is what we're going to do. Remember, the Poisson process has independent increments, and because expectation is a linear operator, so we can strike it through. This will be expected value of ns given fs, and this natural filtration will give us ns minus expected value of a constant given fs will give us that constant. That's what we have here. So only thing left is going to be nt minus ns given fs, and that nt minus ns gives us another Poisson process. Remember, independent increment. So this is another Poisson process within time t to s. Okay, so that will also give us a lambda, or a mean of what? Lambda t minus s. Okay, so as we do that, we simplify, we realize that this is negative lambda t plus lambda t when we expand here, minus lambda s. So this will cancel with this, and then we are left with ns minus lambda s, which is the same as ms, right? So this has proven that mt is a martingale. All right, good. So this is an example you can try for yourself. Yeah, so try this example for yourself. This one you are seeing here. I'm going to wait here for just a second. You see, you write it down. Thank you. Yes, so this is the end of our martingale lecture. So in our next video, we're going to look at the Brownell motion. Yeah, so please don't miss anything we are doing. Martingale, Brownell motion, they are related, so that is, we're just taking everything step by step so that you understand. Thank you so much for watching. God bless you.